Hey, folks. Hope you're doing great. Hope everyone's having a lovely April Fool's Day. And that you've not been pranked too hard, too many times. Last year we did a blog post for April Fool's Day to say Jank was renamed to Grady. And a lot of people believed it. So this year I decided to give everyone some respite from the shenanigans. And next year I'll just hit them hard. When they least expect it. I don't know what we'll do yet though. Maybe jank targets C instead of C++. Just C++ is too difficult. Forget all this. I'm sure the game industry and other industries where C++ is the de facto language will understand. What are we doing today? So we're 2 weeks. Yeah, we're 2 weeks into working on Jank's IR, support for our own IR. And we have we can do some stuff with it now. We can do some stuff. So let's, A and 5, for example. So if we had a function foo that gets A in a binding and then prints some stuff, I think this will work. Let's see. Yeah, so we have the literal 0, we have the literal foo, we have the literal 5. These are all values. This is our IR. Then we create a vector with 0, which is 0, and 2, which is 5. So there's our vector, which is v3. We grab print line, we deref it, we call it, we give it v1, which is this foo keyword, and v3, which is our vector. And we return the result of dynamic call for a print line. So in other words, we return nil. So yeah, like we had all that, but what we have now is C++ code generation. And you can actually see when you take a look at this, the instructions for the IR here, you can see how they map to C++ like pretty fucking directly, right? So he's like, okay, here's a literal with the value 0. It's going to have this type integer ref. And so, and it's called v0. So we do v0 and then we just use auto because we don't need to specify a type. And we just call make box here to allocate our 0. And then here's our v1 is a keyword. So here's our v1, we intern the keyword, and then same thing, v2 is the 5, and then for the vector, persistent vector of these two values is v3. We just take v3 and we do a make box on persistent vector, we give it 0, 2. So like the code for C++ is, at least in these simpler instructions from our IR, is not a bad translation. Like it's pretty straightforward actually. But the problem is when we start getting into more complex instructions, we need to start piecing some things together. So right now, all of these instructions that we're seeing here are within one block. And that makes things really easy because we just loop through the instructions, generate each of them into some C++ code, and then just ends in a ret. So we generate our return here and then done so, right? But as we started to see, as soon as we have like an if, or we have a case, or we have some other stuff, then the control flow ends up being a lot more complicated. I think we also have, just so we could do this, I think we also have the ability right now to do something like size S. I think we can do this. Let's see if this works. Because I ported basically all of this C++ generation. So yeah, so we get a value. This is our meow, which ends up being v0. Well, actually we grab the function first, and then we call the function. That's our v0. It goes into v1. Then we have a constructor call. So you see these namespaced keywords now. These are new guys that have shown up. So we have a constructor call that is constructing a standard string, and we give it this v1. And this v1 is here. We see this character array, and so that's our meow. Meow here, and then we have a character array of 5. That's MEOW, and then new line. Not a new line, but null. And then we have a member call. So we're calling size, and the first argument is actually just the object here, the invoking object. So that's our standard string. And then this gives us back a size type. Great. And then what I did here also is, you'll notice we have an into object. So I created specific instructions for converting native values into jank objects, and then a specific instruction for converting from objects into native values as well. And so this is going to allow us to write optimization passes that check for things like, are we converting something into an object and then out of, from an object, sort of back to back? Are there like conversions that are happening that can just be elided? And then similarly, the other way around, if we go from an object and then back into an object again. So having those as clear instructions in the IR is gonna make those optimization passes easier. So yeah, like this is all C++ land here, like grabbing meow, creating a standard string, doing the member call. And then right here, you get to see like, okay, so now we're getting into like jank object land, because now we're going to take v3 here, which is a size type, and we're going to convert it into a jank object. And then we can grab print9 var deref it and do our dynamic call on that. So yeah, the generated code here is also correct. So like we construct a standard string here. We give it our array, we call size on it, and we haven't done the code gen yet for the conversions, which is why we end up doing a v4 here, but you'll see there's no actual v4 code generation done here, so we need to do that. But anyway, we're piecing a lot of this together now. And today we're going to resume. Today we're picking up on that, and we're going to resume. All right. So I also would like to look into this branching stuff and see if we can figure out how to actually tie all this together. Because as soon as, I'll show you, as soon as we do something like this, so here's where we're just going to return nil. A0, and then if A is equal to 0, and then give me B as 0 or not 0 keywords. So the IR for this will work fine, but code gen for this is not going to work. And in fact, it's going to crash, and that's expected. And that's because we just have we have all these blocks that we need to now worry about. We're not just running through one block and rendering those instructions to C++. Now we have to actually go up a level. We need to take these blocks and their control flow graph representation. CFG is the term we were talking about, and try to turn that into a C++ if else. And I've been considering how to generalize this algorithm. It gets kind of tough, I think, when you consider that if can be nested, like arbitrarily as well. So we're gonna need to know what the final merge branch is, I think. Because we're going to need to know how to resume generating C++ code in the right spot. But anyway, we won't jump into that yet. Let's warm up. Let's warm up and do something a little better, a little easier. What was I just talking about over here that we could do? Oh yeah, conversion. So let's do that. Whoops. So conversion, we're gonna have so into object. Yeah. Oh, we also don't have unsafe cast done. Do we have cast? Yeah. So code gen processor, CPP unsafe cast. Yeah, so actually we can port this guy. This guy's just was unported. So this is just porting from the original C++ code generation that we had from the AST. And it's going to be very, very straightforward. We already have the generated name. Oh, my laptop died. One sec. Come back to life, laptop. Live, be strong. Do your thing. Breathe. I can't even move the mouse. There it is. All right, set. So for this one, we just need to grab inst b. Each instruction has a name, which is the return of this. And so we don't need to worry about being in return position and value. And we have the original expression as well. And that's it. So an unsafe cast is just a C-style cast. So we say autoconst and then the name. And then we do a C-style cast right here to the qualified type. So if we're casting, let's say we have like a unsigned char. So we'll say so we unsigned char, we want to cast to a char, pointer to char. And then this is a pointer to unsigned char. We'll generate basically something that looks like this. Oh, I guess we'll have parens around this expression here, but that's basically what we're doing there. So that ends up being really easy. And yeah, so we haven't done these guys, into object and from object. In AST land, these were just called a CPP conversion, like so. And then they were one AST node that had a policy, and the policy was said which direction we were going. Where is the policy here? Void any object. We check the policy here in a ternary and then just decide which one we want to go to. Yeah. So I suppose we could just reuse this code. Dun. Well, we'll see. So first off, we can delete all of the return position shit because we don't need to worry about that. And here we have scrolled up too far. Beep. And so we have this. We don't generate this. We don't generate that. And then we have the expression inside of the instruction. And so here we already have the instruction value. And here we have the expression here. And this would be, I think, analyze conversion. And here we have the instruction value. And that's that. So this code, as it's written, will be exactly the same for into and from. So that means that from a, that's an int, from here, ideally we can just call gen with our from, but we'll need to build from here. So from const, actually, I don't think that can be const. And this guy from object. So constructor needs name value expression. Yeah. So name, we're just going to take the name from name. Inst, we're going to take the value from that, and then the expression we're just going to take from that as well, and then that's that, and then we can grab the address of this guy, and then I think we're going to need to make an IR inst cpp from object ref from that, and then we should be good. All paths will call itself. Ah, right, because I already have a from. We want to make an into. My mistake. There we go. So yeah, these are useful to have as separate instructions. So even in the AST, it's just one node. It's just a CPP conversion expression. But in the IR, I wanted to have, we don't actually have it here, but we had it scrolled up. So we have this into object. I wanted to have separate into objects and from object instructions in the IR. So that way it was going to be more straightforward to write optimization passes that can collapse those if needed. And it would be possible to do that if we had a parameterized like conversion instruction. I just wanted to keep the instructions simpler. So far, we don't have any other instructions that behaved in that sort of parameterized way. Okay, so that was the conversion. Let's take a look at how this would look. So we should be able to get two conversions. How can I trigger two conversions here? This one won't quite work, but if I did a CPP cast to std string here instead, that would work. Yeah. So here's a from object, and then here's an into object. So we have a literal, which is a jank string, and this is a persistent string right here. And then we do a from object into a standard string here. And so basically we forced a conversion from a jank string into a C++ string like so. Going forward, I'm hoping that we can make literals just be C strings. And then we'll make literal strings be C strings, and then literal numbers will just be like native values as well. Right now they're not. Right now they're jank values. But so we can go from meow, we'll do a from object, and then that's going to give us a standard string here as v1. Then we can do a member call on that for size. Then that gives us this size type. So we do an into object. Ideally, we should have more type info here on this into object for what the actual outcome is. I would expect that this would be an integer ref, and we could use that type information. I don't know why this is object ref right now. Hey, Tinley123, welcome to the stream. Hope you're doing great. And anyway, when we look at the generated code, we can now see, so we grab our boxed string right here. We do a from object. So we actually have this conversion trait, right? And so here's a trait for standard string. We do a from object. That's perfect. And then v1 is a standard string. We do size on that. Gives us v2. And then we take v2 and we say into object, where our conversion type is unsigned long, which is just it's just an integer value. And so this is going to end up being a jank like I64 when it goes into an object, because that's just what boxed objects are. They're all I64s. And then we grab print line, and then we can, yeah. So this all works. That's great. And we just hacked that up. Pretty easily as well, because we were just able to take it from the existing C++ code generation. So let's see, what else did we need to do there? There was, I think before we jump into the branching stuff, there was one other thing I wanted to do, which is if we had something like a code and then CPP exit for code, we could take a look at this. And so we'll see here that we have a literal for value 0. We say, I want to convert this to an int because that's what the argument is expecting. So we do a from object conversion. We convert that to an int. Then we take the value of this function, which is exit, and it has this type. And then we do a call, CPP call on that function with our v1, which is our int. And then we take v3 here, which is actually void, and we convert it into an object ref. So this is a sort of thing that can be optimized away as well. Actually, this doesn't even render here. Why is that? Yeah, so we'll have to figure out how to actually handle this, because we're gonna want to make we're gonna need to like turn into objects from void into just nil. We should probably just not generate those in the IR, because it doesn't make sense to take, you can't have an instance of a value that is void. So like this can't quite work. So although every instruction has a name here, which is the, like the value that, or the name that corresponds with how you refer to that value, you can't actually use v3 anywhere, because exit, this function here, assuming it didn't actually exit, either way, it has a void return type. And so v3 is not actually something that can be used. We need to account for that. when we're generating our IR. Do we? Maybe we don't. Because I think that our conversion trait actually handles void. So convert built-in void. Yeah, so we do have a conversion for void that doesn't take any arguments and then just returns nil. So actually, maybe we just need to account for this in CodeGen when we're converting into object. Hey, Twitch DD. Into object. Ah, yeah, we have void here. If yeah, but this isn't quite doing things correctly because this is based on how we did things in the old way. And we need to do things better here. So what we'll do here is we'll grab this and do this. How's your day going, Twishity? And we'll do this like so. And so that'll give us our actual value. This should fix the issue. And so we'll end up getting a v4 that's actually just nil. And then we can return that. Am I still planning to do my own jank IR? That's what we're looking at right here, Twitch DD. This is Jank's IR. So this is the third stream now where I'm working on Jank's IR. It's been 2 weeks. Man, this IR is jank or something. Ha! Ha! How's it going, Matt? Hope you're doing great. Cool, yeah, so now when we try to do an into object from a void value, we're just going to grab a nil. And so we end up doing a code gen for v4 that gets us a nil, and then we can just return that. Perfect. Perfect, perfect. Doing well, hope you're doing well as well. I am. Thank you. Yeah, Toshidi. So this is we're about to see some more because we did our warm up. Now we're gonna jump into something that's a little more complex because I have basically all of the. Well, we can take a look. Yeah. So when we look at these gen functions, I have, there's constant, I have gen for def done, gen for var deref, gen for var ref, gen for dynamic call, literal, persistent list. So this is all like the C++ code generation functions, persistent vectors and array maps and hash maps, hash sets. So I need to do functions and closures and recursion and let fun and then jump and branching. But I have throw, try and catch and case need to be done. I have ret, and then I have all of the C++ stuff from C++, CPV raw, CPV value, into object, which we just did from object, CPP call, constructor call, member call, member access, built-in operator calls, CPP box, unbox, new, and delete. So all of these are done. Really, we just need to do the branching related ones. I think if we can figure this out with if, then we can and make sure that it's properly generalized so that it works with arbitrary nesting. I think we can figure it out with the rest. But I'm not yet I'm not yet sure if we can figure this out without needing to like go back to our IR and make sure that we have more information ahead of time for code gen. Hey Twitchy Mall, what sort of lang is jank? Jank is a Clojure dialect for native. So if you're familiar with what Clojure is, then that probably gives you everything that you need. If you're not familiar with what Clojure is, then take a look at Clojure. It's a modern-ish Lisp that aims to be very practical, functional first, with persistent immutable data structures and a really rich standard library for pure data transformations. And Clojure works in tandem with its host. So the de facto Clojure implementation is on the JVM and interops with any Java library seamlessly. But there's also Clojure on JavaScript, there's Clojure on the CLR, there's Clojure on Beam, there's Clojure on Python, Clojure on Go, Clojure on native, which is what we're building. And so Clojure is like this language that's kind of designed to run in a whole bunch of different environments. And in each of them, the Clojure dialect for that environment really embraces that environment. And so an example of this is like Clojure itself is never going to have like socket programming, like for networking or file system stuff as part of the standard library. It's just not going to happen because it's always going to rely on whatever the host has to do that. And so on Clojure JVM, we just reach right into the JVM libs in order to do socket programming or work with file systems. In Clojure script, you would reach right into JavaScript's WebSockets or if you're, it's like Node, then you would just use the Node file APIs. And same thing with jank. So with jank, which is the language that we're building, it's Clojure on native. You have the whole native world, but you have also a direct interop with C++. So native is just this huge landscape that is really, everything's kind of operating at the C ABI. But C++ is one way to get to native. And jank, when we start talking about native, we come to realize that jank is a Clojure dialect, yes, but jank is also a C++ dialect. And so that means that you're going to be able to define C++ functions within jank that are actually just C++ functions. You're going to be able to define C++ structs and templates, everything like that. Jank already has a C++ JIT compiler, and so you're able to arbitrarily compile new code on the fly, and that includes like JIT instantiations of C++ templates and everything like that. Not POSIX directly, we use C++ runtime, correct. So jank is basically like the whole language compiles down to C++. So we actually that's what we're looking at right now is the code generation that we do. So here's an example. This is the IR that we have for representing some code, and then we actually just generate C++ code. Oh my God, you're naming it jank. I thought it was an adjective. Jank is an adjective in colloquial terms, but jank is also the name of the language, yes. Overview of how IR gets transformed from DMG. IR, well, I mean, that's kind of what we're working on right now. Like the transformation of IR right now that we have is pretty much 1-to-1. So what was an example that we were looking at with, something like, something like, this was a really simple one. So we had some code where, what were we doing? Where did that go? I thought I had like a vector. Yeah, anyway. Let A is 5, B is 10, print line, foo, A, B. So we have this function foo, local bindings A and B, 5 and 10, and then we have a print line call. This turns into this IR. This is for damage. And so A becomes just this V0 here for 5. B becomes this V1 for 10. We also grab the literal foo, which is the keyword that we're going to be printing. We grab print line, and then we have a dynamic call. So each of these is an instruction in the IR. And then this maps directly to the C++ that we generate. So, the V0 for grabbing value 5 is like, take the value 5, box that into a jank object, take the value 10, box that into a jank object, take the keyword foo and intern it in the runtime, take the print line var and intern that, and then do a dynamic call on all of that. So like, this is like a 1-to-1 map. Like you can just look at the symmetry between these instructions and the C++ that is underlying it. And the reason for that is, like, I have specifically chosen the IR that we're working with to work at the semantic level of closure. So jank is built on Clang and LLVM. Like, we're generating C++, we're giving that to Clang to JIT compile, which it will turn into LLVM IR, which is a much lower level IR, and then we'll give that to LLVM and the JIT runtime in LLVM. But the IR that we're working with, that we want to try to optimize, works at a much higher level, which is what we're seeing here, and that maps almost directly to the code that we're generating. What's the process of doing that? I mean, the process. So like for what we have right now is just we have this structure. So we have this whole thing is a module. Modules have functions, and then this whole thing is a function. Functions have blocks. Blocks have instructions. And what we end up doing is for each function, we loop through all of the blocks, and in those blocks, we loop through the instructions, and we end up doing the string building in order to build up the C++ code. So we have this IR module here, gen CPP. We build this helper builder. We start looping through all of the functions here. We do a gen for the functions, and gen for a function is going to here do some string building to here we're generating the extern C, the return type, the name, the implicit parameter. We're generating this line, right? This initial line. And we handle all the parameters and their types. If we because we have closures as well, we need to deal with whether or not we have a closure struct that we need to be working with, and then we start looping through all of the blocks. And so the block iteration is what we're going to be improving next, because we need to handle dealing with branching and merging and following the control flow as it goes through. And so let's jump into that. DSPX, PLCR, thanks for the follow, and Twitchy Mall as well. I don't think I missed anyone else's questions. Just checking. I think I got it all. How jank we talking? Super jank. Super jank burger. So let's take a look at what happens when we do branching. So let me, oh wait, did we ever fix that? No, we didn't. We didn't fix that, that other thing I was looking into because we got distracted with chat, but that's fine. We can jump into branching now. Get that another day. So in this example here, we have A is 0, B is the result of this branch. And so we check if A is equal to 0, then give us this keyword, otherwise give us this keyword. So the IR for this is totally fine. And we end up doing our equals check, and then if that's truthy, then we branch to if, and then otherwise we branch to else. And then we have this phi epsilon mechanism to get us back to this merge and grab the value from each of these branches. Now, what we need to do is, when we hit this branch condition, we need to know how to put these three blocks here together into an if-else sort of setup in C++. Hey, Ben Chilling. How you doing? Now, the problem that we have right now is that we don't actually know how these come together, because when we take a look at the branch here, we have our then, we have our else, but we don't actually know the merge for these. And so I think that we're missing some information here from the branch, because I can't know easily anyway where these are going to come together, or if they're going to come together at all, because sometimes they won't. If we're in return position, then the if and the else are each just going to end in a return terminator. They're not going to end in a jump. And so in that case, we wouldn't actually have a merge. So what I want to do is I want to go back to our, I want to if ref. I want to go back to where we're building our IR for this, and I want to add a merge member to this branch instruction, so that way we can know if there is a merge, what the actual label is. And then this is going to allow us to say, okay, now let's start processing our if and our else and know where we're going to end up in order to get our merge done. Ben Chilling, amazing, and Mew, I'm great. I am doing very well. So here's where we remove our merge block. So yeah, if position is not, okay. So this is, I think what we'll do here, because this is where we're creating our branch, I'm just going to say if the position is not equal to tail position, meaning we are going to have a merge, then we want to just keep track of the merge blocks. So that would be block name and merge block, this guy right here. And then otherwise, we're just going to specify none there. And that's because, so we're going to jump to our IR builder, and we're going to jump to branch right here, and we're going to take in an option. And this option is going to be of an identifier, and this is going to be our merge block. BLK is what we were calling that for everything else. And jump back here, and there's that, and then merge block right there, forward that on, and struct branch, and that's that. And then here we go. So we're going to take this This is our option. I wanted this guy. And then this is merge. And then we had this here. This was merge and JTL option. Okay. That pipes all of our information together. And now we just need to do the printing of that. So if we have merge, else, so we'll say merge block unwrap or something like that, maybe. I don't know if that is accurate or if that was because it compiled too early. We'll see. Apparently it is. Yeah, that's fair. So we probably can't use a ternary there, but what's wrong with this one? Instruction 204. I added this branch. Yes, that looks right. And this. Yes, that looks right. What's the problem? Semicolon is the problem. When you mentioned IR, I imagine you only have one LLVM IR. No, so Ben, the thing that I've been working on the past 2 weeks is adding a higher level IR for jank, and that is this. What we're looking at right here. So this IR is something specific to jank, and it works at. It represents things at a much higher semantic level compared to LLVM IR. And so we go from jank source code to the AST, lexing, parsing AST, and then we go from the AST once we verify that okay we have a valid program here. Then we go to our IR, and then that would be optimization passes on the IR. And then we go from the IR to CodeGen, which is in C++. And then the C++ we give to Clang. Clang will then convert that to its own AST, and then it will go from the AST to. There's actually Clang IR as well, which is not yet being used, I think, on main, but will be eventually, probably. Which is MLIR based, and it's Clang's own semantic, like higher level IR. But ultimately, it ends up being LLVM IR. Yeah, so we optimize things like the optimizations that we're going to worry about are not going to be low level things like register allocation and the other like lower level like people optimizations that Clang is going to do for us on the C++. We're just going to let Clang do that. Why would we not let Clang do that? The optimizations that we're going to do are going to be things that make sense in closure land, like removing var derefs or removing. We were talking about this like from object and into object conversions that go from native objects into boxed jank objects. And so if you have like some value that you're taking from a boxed jank object into a native value, and then you're going back into a native value directly, like why not just elide that and use the original value anyway, since we know that those are going to be those are going to round trip. And so this is the sort of thing that LLVM, like Clang and LLVM, are never going to be able to optimize for us, because it's way too, this is way too high level of a concept. Clang and LLVM are going to just see like C++ calls to the conversion trait. They're not going to be like, oh, okay, well, you were converting from one thing to another thing, and like there's no need for you to do that. And so that's the benefit of having things at a higher level, is that we can detect those things. And also things like var derefs, if we want to elide those within a function. You know, if you're calling a var you're calling a function through a var a bunch of times, you don't always need to like deref it for every single one of those calls, especially if it's in a loop, you know. In some cases, maybe you actually want that, but not all cases. Okay, and then we had this other one, IR processor, where we can't use this here because the types don't match. How do we don't have a good way to construct. Yeah, well, at the very least, we could just say identifier like so. What's your most favorite features of jank? I have not used Clojure, by the way, but I wonder what I'm missing out on by using C. Well, I mean, C and Clojure are very different languages. You know, like C is a systems programming language. Clojure is like a dynamically typed, polymorphic, garbage collected application programming language. They are like categorically worlds apart. Okay, so now we should have a merge here. So we do have a merge here, but why do we not get anything printed there? We print our else because we don't have this. So that's a tough thing to answer, Ben Chilling, because I mean, I really like Clojure for reasons of like its data, like makes it really easy to build programs around data transformations. And ultimately when you it can be difficult, but when you shift your mind that way to think about designing any program as just data moving through a pipeline of transformations, like, oh, the user's playing a game, right? So they move the mouse and they click and they click. And like the user events, well, that's just an infinite sequence of data, right? And those events are each a little packet of data that's in Clojure. We just represent with maps and keywords and vectors like this right here, this output. This is Clojure data. This is the exact syntax. Like this is all valid Clojure data. And this is how we would represent things like user inputs. And so, you know, user clicks here, does WASD on the keyboard and space and everything like that. That's just a sequence of data. And then you have all of your objects in the world, and they're moving around and they're interacting, and all of those just represent with data. All of your logic for moving your NPCs around or handling environmental effects, everything like that, are just taking your old game state, modifying it to give you your new game state. And Clojure builds this all around immutable data structures, which gives you a lot of sanity guarantees. For example, if you wanted to write a multi-threaded renderer, of course, I'm using games for all these examples because it's just very easy for me. My background is in game dev. But if you're modeling your game around this persistent immutable data, then when you go to render, it's very easy for your renderer to just take a snapshot of that data and know that it's not going to change. in fact, it doesn't need to do anything different. Whenever you have a handle to some data in Clojure, assuming you're just building on maps and vectors and strings and keywords like we are here, it won't change, period. It just won't. It's immutable data. And so that means that categorically you can rule out all of the synchronization and race conditions and bullshit that you would need to worry about normally if you wanted to render on one thread and then have your game loop running on another thread. You just don't need to worry about that. And also, if you wanted to do things like save the game state each frame, so that way you can actually have a slider on your game where you can fucking rewind. That becomes trivial as well because your game state is just represented as data. Do I think that other Clojure implementations could use the IR optimizations? Yes, I think that the IR optimizations that we're going to be doing are going to be like not specific to jank. They're going to be Clojure-oriented optimizations. However, it's all going to be written in C++, and so like in practice, it's not really going to be usable by anybody, but this approach could be. I imagine that the other dialect devs are going to let me like figure out all the details and see if everything works and if it's overall worth the effort. And then if it is, then maybe they'll, some of them will follow suit. But, and I'll be happy to provide info on how to make that easy for them. Okay, so what we have now is we have the merge info here. And so this is the happy case where we have merge info. As we'll see in a bit, there are some cases where we don't actually have that. Now I need to figure out when we, not here, but here, when we're actually looping through these blocks. Yeah. Now this is the hard part. This is the hard part. We're going to loop through and we're going to find a branch. We're going to find a branch right here. And then we want to turn this into an if-else. And so we need to know three things. We need to know all the things, all the code, and that's blocks and instructions that belong under the if. And we need to know all of the code that blocks and instructions that belong under the else. And then third thing, we need to know when to stop, like when we're done with the if, what comes after the if, and that's the merge. Not easy to condense the REPL to folks. Yeah, you notice, DMG, that like I didn't even bring up the REPL because it's just a sort of thing that I have found explaining doesn't really do justice. I have tried explaining REPL-driven development to non-Lispers, and I've never had anybody get it. And like I'm generally pretty good at explaining technical things, and I've had like nobody's actually come away with, I think, a sufficient idea of what it's actually like. I think that you really need to see somebody do it. will I be showing off REPL-driven dev on my streams? Absolutely. So right now we're writing C++ because we're working on the compiler, and the compiler is all written in C++. The compiler and runtime are all in C++. But at some point, we're going to be writing more jank than C++, and at that point, I'll be using REPL-driven development in jank. The point of REPL-driven is that you're testing your code in real time while programming it? ? That's an aspect of it. I wouldn't say that's the point of it. I think that the point of it is so that you start up your process, whatever it is, your game, your application, your web server, whatever. You start up your process and then you connect to it from your text editor. And then you can send arbitrary chunks of code to either iteratively develop your application or debug your application, right? You don't need to do a print line, add a print line for like what some value was, and then try to like read that from your logs. Instead, go into that function right where you would normally add a print line and add a def, right? Add a def that actually defines a global variable that stores the value that you were working with. And then like do your normal user action that triggers that code path. And then in your REPL, go back to that def and evaluate the var that you just defed. And now you have the actual value. And the nice thing about that value is you can actually just work with that value. And so, especially since Clojure is built around immutable data, you can actually work with that value and start transforming it. You can, you can print it. That's the simplest, easiest thing to do. But there's so much more that you can do because you have access to all of the data. So that's a hard thing to convey because it requires understanding like data-oriented programming in the sense of like writing programs with immutable data. And that's already something that most devs don't grok. And the REPL kind of builds on top of all of that. If you build your code in real time, I guess you have to be idempotent, otherwise it's kind of chaotic. Yeah, well, so in Clojure and in Lisps in general, but definitely in Clojure, we end up having design patterns and libraries and everything like that around like REPL-driven workflows, and like we design our code so that it can be easily used from a REPL. And you can tell the people who do this and the people who don't, right? And so if you have a web server, for example, that needs to connect to a database and Redis and some like JWT, like identity provider, all these different things that you have as resources, then you might use a library like Integrant or similar in order to ensure that everything is like bootstrapped sufficiently. And then you can have kind of triggers to reload certain things on demand from the REPL. So that way you're like, okay, I've just changed this crucial part that needs to reconnect the database, and like that stuff can just automatically happen. And yeah, I mean, since the REPL is such a crucial part of Clojure programming, it makes sense that we wouldn't just it makes sense that we would design our code around using the REPL. Okay. Anyways, I gotta try to make some sense of this. So we have a branch. We have a then, we have an else, we have a merge. So as to reapply all actions, events since the beginning to avoid a situation where you apply some functions to a global state that is then deleted later. Yeah, it is possible, Ben, that you get into a situation where you've defined some things in your REPL that, for example, never actually got saved to your project. And so things work in your REPL session, and then when you tear it down and you spin it back up, it doesn't work anymore. That's possible, and it does happen, especially for like newer REPL users that aren't just familiar with how to like good workflows around that. I think that in my experience, as I became more experienced, this just wouldn't happen. And the reason is, like, when I'm writing functions in the REPL, I'm actually changing the source code where I want that function to be. And I'm writing a defin, or I'm changing an existing defin. And then I just evaluate that defin, once I save it in the file. Or I'll evaluate the whole buffer or whatever. And I actively work to keep, like, the code as it's written, mapping the code as I want it to be in the process. And that way, if I need to tear things down and I spin it back up, then I have everything I want. And DMG, if I want something temporary, then Clojure has these rich comment blocks where you can put code inside of a comment block and evaluate that, and it'll work well with the REPL, but it'll never be evaluated as part of your actual project. There is no replaying. There's no replaying that we do. So the replaying history is not part of my or anyone else, like any Clojure dev I know. It's part of their workflow. So I'm looking at how this comes together, and I think that we need to change the way that we're looping over instructions and blocks, because we need more flexibility. Right now, we're actually just looping over all of the instructions inside of the current block. And that's it, actually. We're just looping over we're just looping over the first block, because I just wanted to get something working, right? And I knew that I could fill in most of the C++ generation with just one block and get it, like, to a point where it worked. And then I could worry about the blocks, because they are isolated concepts. And the way that I see this working is, so we're going to need something similar to this, except I think we're going to need to keep track of, like, the current instruction and block that we're iterating over inside of this builder. And the builder is basically keeps track of the buffers that we're building up, and points back to the module that we're working on. But basically, this is our scratch pad of state. And so I think if we have something in there for the instruction index and the block index, then what this will allow us to do is, when we hit a branch, then the gen function for the branch instruction is going to take over, and it's going to start iterating through all of these itself to the point where it finally hits the merge, and then it's going to hand control back over to whatever like higher level mechanism is iterating through all of the instructions. I think that's how we'll do it. Now, it's possible I have this voice in my head that's telling me like, maybe we're not going to be able to have a higher mechanism that is going to like be our fallback for looping through all of these things. And maybe each of these gen functions is going to be responsible for incrementing things one step further. That way we give full control to the generation of each instruction to consume as much as it wants to consume. But I would try to avoid that if I can, because it's just easier to fuck up if you have to deal with like moving forward in all of these different places, especially with like early returns and everything like that in C++. Not in the IR, but in the actual C++ code that's working on the IR. Okay, there's my sugar and my caffeine. Now we're on to water. Okay, so I think that if we were to shoot, where were we? Yeah, we were in Builder. So here, if we have something like a usize probably for block index, and then also instruction index. Yeah. That will probably, yeah. And so we don't do a range-based for loop. So right here, we don't do a range-based for loop. Instead, we do a while loop probably, because there's no need for a for loop given that we already have our value. So we would just say while the instruction index is less than block instructions.size, then b instruction index increment. And then so here we would say block instructions instruction index. And then we automatically increment. So yeah, the reason why I'm wondering if each gen function needs to increment manually is like, I don't know actually if we can get away with this automatic increment in some cases. Like in the case of the branch, we're always going to make sure that we need to end like one instruction shy of where we want to go next. And that may not always be viable. We'll see. Just some like yellow flags that are tripping up in my mind. All right. Okay. So this should have effectively the same behavior as what we had before. I just want to make sure that this works in like one of the simpler cases that we were doing. Let me close this and then do something like this. This did work before and it still works now. Great. Cool. So let's go back to this, and then now, so this is the one that crashes. Yep. And now let's find out where we're crashing. Just make sure that we understand that, because I don't actually know why this is crashing. I know it's wrong. I know it's incomplete, but I don't know why it's crashing. Oh, gen. Is this when I just see gen, like when I see the repeated gen here, this makes me think that we're actually Stack Overflowing. So if I do a backtrace here and I continue and I let it go, yeah, we are. So look at all of these stack frames, right? So we have like almost 18,000 stack frames. So we're getting stuck in a loop. There must be a branch here that we're not actually supporting. Do we not have branch? Yeah. So we do have branch ref here and we return none. Why would that? So the instructions, we take a look at the instructions we have truthy, dynamic call, var, deref, branch. Do we have truthy here? Ah, ha, 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 ha. We do not. That's the problem. So truthy. If you wanted to use the REPL on a game, what system might you program while the game is on? Let's say a Roller Coaster Tycoon game. If you don't have a history buffer, then it means you're just modifying the current state. I don't know the limits of what. So Ben, check it, brah. So what you would do is the REPL. Don't think about the REPL as being used to modify state. That's not really what we use it for. You can, but that's not really the point. The main point of the REPL and REPL-based workflows is to modify the code, the program, right? And so Clojure has mechanisms that allow you to redefine functions arbitrarily, like at runtime. And so if you wanted to add some, yeah, I'll give you an example here, Ben. So let's say you're building this Roller Coaster Tycoon game, okay? Now to start with, you're showing your game world, but you don't yet have any UI. And you want some UI that shows the current cache amount you have, as well as the current number of visitors, as well as the overall happiness rating of your visitors. And so you have a render function, and your render function is currently rendering the scene. And then what you do is you jump in, you're in your text editor, and you jump into your render function and you add a new call. And you add a new call to a function called like render UI, right? And so you define this new function, render UI, and you call that inside of your general render function. Now inside of your render UI function, You then use, you know, like IMGUI or whatever UI library you're going to use to render the, you know, background of your bar that's going to hold your information, and then the text for the various bits of data you want, and the calculations for that data, everything like that. And then all you need to do is you can either just reevaluate the buffer that you're in, or just evaluate those two functions, since those are the two that changed, and you will send that new code to your running game. And that means that the next frame that you go to render, because every frame that render function is being called, well, the next time that render function is called, it's also going to, like it's going to call the new render function, and the new render function is going to call the render UI function after rendering the world. And now you're going to have UI rendering on top of your game. And all you had to do was write the code that you wanted to render the UI and send it to your running program, and the next frame you're already getting it. And so you can repeat that process to iteratively and interactively build up all of the UI that you want without restarting your game. Because your game basically is always going to be doing what the latest, version of the code that you send to it tells it to be doing. So hot reloading gets you a lot of the way for this. And so a lot of game engines these days, even the native ones, have some form of hot reloading. And with hot reloading, you can achieve everything that I just said, but it's not the same as the REPL, because the big difference with the REPL is what I was describing before, where you have complete access to all of the data in the program. And so if you wanted to just grab the data that represents one of the people who's walking around, and you want to understand, like, oh, why is this person stuck, or like why did they choose to go on this ride instead of another ride? You're able to just grab the data that belongs to them on that particular frame, and that's a snapshot of immutable data. And then you can start feeding that in manually from the REPL. You can start calling certain functions that you use in order to decide where a player, where a NPC should go next, and you can use that to figure out like what's wrong with your functions, or what extra logic that you need. Let's say in render UI we put cache plus equals 10, and we started with 0 cache. If later we choose that we don't want that line, if we remove it, we'll be stuck rendering this high amount of cache, right? Since we ran the game for a couple of minutes. If you're putting effects that change state inside of your functions, then yes, those are going to change the state that persists in your in your process for the lifetime of that process. Correct. But that's kind of mixing mindsets. There's a mindset shift when it comes to modeling around immutable data, which would make you not just do cache plus equals 10. We'll probably not even have the capability of doing cache plus equals 10 inside of your render UI function. So if for some reason you were able to do that, yes, but as Taco T said, like the render UI function should be effectively a pure function from the perspective of your game state. Like that's not even going to be something that is that's possible. Okay, so we should, nice, now we don't crash. All right, now we need to get the code gen for truthy in order for this to work, because what we can see here is we have 0, we have 4, we have 5, we have 6, which is our dynamic call, and now we need to get 8, which is a truthy check, and then we can do 9. So let's just get our truthy check done, and for this I'm just going to jump and grab that. And okay, so for truthy, we just want to say this is equal to this, pretty much. And so this will be inst, this will be b, inst name, and oh right, we need to actually call truthy. So jank runtime truthy. There we go. And here is our value. And here we return inst name. That's it. That's truthy. Yeah, Ben, I really hope to be doing some game dev in jank. It won't be this year, realistically, but next year, when jank is stable and ideally production ready, I would really like to be getting back to some game dev in jank and demonstrating how to build games using immutable data structures iteratively from the REPL. It's I'm gonna blow some minds, you'll see. And then we're going to do that, like, and jank will be a Clojure dialect and a C++ dialect. And so we're going to be able to drop down to C++ performance whenever we want within jank. And then otherwise, we're going to be able to take advantage of the polymorphic runtime of Clojure. And it's all going to work together in one language. It's going to be fucking great. It's going to be fucking great. Okay, so here's our truthy. And all we do is we just grab v6, we call truthy on it. That's going to take in some arbitrary jank object. It's going to give us back a bool value. And so that's our v8. And now we're on to branch. And so here's branch. So in branch, we have the if, we have the else, we have the merge. And we have our condition. So let's first just generate our condition, because at least we can do that. And I'll still just generate, I'll return none for now. So we're gonna wanna do, oh, not that, we're gonna wanna do one of these, and we'll do an if on that. And we'll do that. I think it was called cond. Was it not called cond? It was called condition. For the situations where you add effects during runtime, you might have something like pressing escape and restarting a level, or you might transfer location to reset root. Sure, or I mean, like, you just have a function in the REPL that that sets your state to whatever you want as well, right? And so, like, whatever the user might press is just going to call a function behind the scenes, and you just call that function from your REPL. That's really easy. Okay, so here's our if. Now we don't know what's going to go in there. We're going to do our else, and then there's our else, and then we're going to return yeah. And then we're not going to deal with the value assignment yet. Condition, yeah. Does it switch the code at the end of the frame, or could it split a frame like a preemptive scheduler? I mean, a REPL is just gonna do the work on demand. So that could be in the middle of a frame. And Clojure is specifically designed around this, and so function calls, like functions, can be redefined at any time because there's automatically a level of indirection. When you call a function, you go through a var, and functions exist inside of vars for the most part. And so each time you call that function, you deref the var to get the latest version of the function. And so that means, and this is automatically synchronized. Vars, the root of a var is atomic, and so whenever you redefine a function, that's an atomic operation. Whenever you deref the function, that's an atomic operation. And so all of this is thread safe as well. Like when you do this from the REPL and you redefine this code, it's happening from another thread, but it's still it's thread safe because it's all atomic, and then it ends up affecting all other threads as soon as the operation completes. These are the sort of things that you just don't need to worry about in Clojure. They just work. Okay, so here is where we want to start progressing the builder. And so we have our check. Here's our condition. So we have our branch on V8, and 8 is the result of truthiness here. And then we need to take all of this and put it inside of our else, and we need to take, all of this, put it inside our if, all of this, put it inside of our else, and then we need to take all of this and put it after the whole thing. And so we're going to be here. We're going to know that there's nothing else in the current block because branch is a terminator. There's nothing else that can come after this. So we need to jump to a new block. We're going to change the builder. It's going to have a block index, and we're going to change the block index to be the index of this if. We're going to change the instruction index to be 0. And then we're going to start iterating. And we're going to go until we find a jump to our merge. I think that makes sense. We're going to go until we find a jump to our merge. And so all this is going to happen in a loop right here. Yeah. And then we'll have to do the same thing from else. Yeah. I'm going to step away for just a minute or so. Use the restroom. Be right back. If you had a thread running a GC on an array and use a REPL to remove the GC, would the thread stop at like iteration 5, leaving you with half compacted array? I don't know what you mean by removing the GC. Maybe you mean removing the array. But no, in general, like the garbage collector we use is thread safe. And so any operations that you're doing are not going to get in the way with what the garbage collector is doing. That's a lot easier when you have immutable data structures as well, which we do. Okay, so let's enter a loop, and I don't know if I don't know what we want yet. Let's just say while true for now. I'm still figuring this out. So here we're going to basically do the same thing that we're doing inside a gen block right here. And I don't know, maybe we do this. Now, do we have inside the builder, we have the module block index. We're going to need to know the current function as well, aren't we? So module, okay, because we reuse the same thing for the okay, this gives us the current function. So now we can do things like yeah, we're going to need something more robust than this going forward. I can already tell, but at least we could start simply. Function blocks, and then we want B block index. Okay, so there's that, and this ends up being instructions right here. Yeah. And then looping through that. Okay, so the first thing that we do here is we're going to set the block index to be the index. All right, so because we're right here, we are block index 0 in this case, and then our instruction index is all the way at the end. We need to set our block index to be this if, and we need to set our instruction index to be 0. Now, how do we get the block index for a block name? We're going to need a linear search. We should probably just add a helper to the probably to the function. I'm thinking like find block, and then we want then block. That is an identifier. Yeah. So we'll jump over to our processor, which is function right here, and we'll say find block, and this takes in, actually we'll just grab this and then we'll call that find block. Find block, that's const. And then we'll jump over to here and we'll define it. And what we're going to do is we're just going to loop through all the blocks for auto const block in blocks if block dot name is equal to name, then return. We can't do this either. We have to have a index. So I is less than blocks dot size plus plus I. If blocks sub I, then return I. And then we need to have a fallback for what we do if it's not found. This should never happen. It should not be possible. So do we fail? Do we panic? I don't like that. Famous last words. Yeah, Robin. Exactly. So yeah, I'm just wondering now, do we affect the return type to be an option for something that should never happen, or should we just handle that case exceptionally? Yeah. A block is a sequence of instructions. Yep. So functions have blocks. Blocks have instructions. We can see that here. So this is a function. Functions have blocks. And then so here we have an entry block, an if, an else, and then a merge. And then each of these blocks has instructions. And this follows LLVMIR as well. Okay, cool. So now we have a find block. We can do a find block there. And that gives us the block index. Then we can start looping through the block indices, loop, loop, loop. Why is there no else if? Else if isn't actually a language construct. Else if is just an else and then an if. And so we have if, we have else, which means we have else if. Else if is just an if nested in the, that's put in the else, right? Python as elif? Well, we're not Python. Okay, so this ran forever. Why? Yeah, Clojure just doesn't have elif, Ben. We use, like, Clojure has if as a primitive, and then cond p, and others as macros. And so Python doesn't have macros. And so Python And also, I mean, Python is just like philosophically quite different. But Clojure benefits from having macros, and so we get to have more semantic sugar without having more language features. Why do I like dynamic typing? I don't always want dynamic typing, but in some cases, especially when we were talking about that sort of that REPL-driven iteration, and then modeling programs like this around data, I think it's a tremendously powerful way of writing programs. And you don't there are no, in C++, if you were to model this, this would be its own class, an instruction class. This would be a block class. This would be a function class. This would be a module class, right? And then each of these has its own parameters and members and accessors and mutators. And you end up with hundreds of lines of code just to represent the construction of these things. And then what if sometimes you want to create an instruction and provided only a couple of things? Oh, you got to overload the constructor for that. You're going to need a couple of different constructors. And so types, especially nominal typing, the way that it's done in C++ and other languages that are similar, really can get in the way sometimes. And in Clojure, this is just a map, right? It's just a map with keywords and symbols and numbers and strings that's in a vector, right? And so all this is just vectors and maps and keywords and stuff. And this allows you to represent data in a really flexible way. And I think that is combined with the standard library of just really powerful transformations of that data. It's a tremendously efficient way to work. Now there are some times when I want types, either for performance or for correctness or for documentation, and so jank allows you to switch between doing things more C++y or doing things more Clojure-y. And whenever you do things in the C++ side of jank, it's all statically typed. Okay, so why are we looping here forever? We set instruction index, we set our block index. Let's just do a breakpoint here and then figure out what the fuck is going on. That was 609, I believe. Yep, 609. Run. And so we're here. Print B block index. Why? Oh yes, currently 0 because yes. And then instruction index. That's currently 5. Okay, yeah, makes sense. So we do this. I'm expecting p.block index to be 1. Yeah, nice. And then that goes to 0, perfect. And then can we grab this whole thing and just print that? Maybe. We can. So instruction size 3, yes, great, perfect. So we want to grab the current block index, current instruction by instruction index. We want to do a gen on that. That makes sense to me. And then we increment. And then we increment. So there were 3 increment. And then we're done. Uh-huh. Okay, and then we're out of here. Okay. And then, and then this ends up being a problem because now we're past the end here, which is kind of what I was worried about, having that general increment at the top. So this is 3. And then the other thing is that our block is not right anymore. Yes. So the block has changed since we started incrementing this. Yeah, so I expected that we would need a better way of just stepping forward. Oh, I thought we could maybe get away with it later. I think we're actually going to have to get away with it now. Or rather, we're going to have to like figure it out now. Fine. Fine. So we're going to need to do that here. We're going to need to do that also in gen block. I think maybe we can just get rid of gen block entirely. You had a global stepper and now you need multiple ones. Yeah, so I think I had this global stepper in gen block, but I mean, that was just the first thing I hacked together to work, to step through one block. It wasn't, you know, it didn't even have multiple block support, just because I'm just hacking together this code gen for the IR. And now that I'm like sort of tying multiple blocks together, I think that the global stepper is probably not gonna work. This was just like the scene blocks and the gen block were just my first like sort of best guess at what I would need. But yeah, it's looking like each gen function is going to step on its own. It's just going to increment forward on its own. Yeah, and so when you're on like a jump or something, then we're just going to, like, it'll be the gen function that actually changes the block index and the instruction index. Yeah. Okay. Let's get rid of gen block. And then we do need some sort of top level loop. We could probably just do it right here. And we probably just want to like loop while we're not done. But how do we measure doneness? I don't know. Yeah, if we do we do one of these here. So we're going to start at the top level and we're just going to loop through one block. Then even if that block changes, yeah. And this is a good rule of thumb for you folks to use less than here instead of not equals. That way, if you do end up going over, like here, if this guy pushes us past the size, that's fine. And our condition will check for that. If you use not equals here, then if the size is 3 and the gen function here moves you to the end, and then you increment, now you're past 3, and then this keeps going, and then you're fucked. So I use less than there defensively. Perfect. So this gives us the code for the if inside of our if. But we don't have branch set done, and we don't have jump done. Okay, not bad. Also, does the branch say what our shadow should be? No, it doesn't. Hey, RMB. What's the current state of the compiler? Jank on main can compile to... Jank on main is usable. And so people are already building... like there's someone building a game engine in OpenGL. Some other folks have done some Raylib SDL stuff. The branch that we're working on now, we're redoing CodeGen, and we're adding our own IR. So that way we can do some more optimization passes on it. Current perf is not great, which is why we're focusing on optimization right now. That's only it's only not great because I haven't worked on it. I haven't worked on perf for the last 2 years. Been working on C++ interop and closure parity. So right now is when we make perf great. What are the paradigms in language? It's closure. Jank is closure. It's a closure dialect on LLVM with C++ interop. So take a look at closure. What's the main code patterns that came to mind that made you realize you need the second IR? Well, so 2 weeks ago, so I've been working on this IR for 2 weeks now. And I've done the translation of AST to, the designing of the SSA based IR, and then translation of AST to the IR, and now IR to CodeGen in the past 2 weeks. But before that, I was looking into the sort of upcoming quarter. And so for this Q2 of this year is when I'm focusing on optimizing Jank. And I was identifying the key issues that I think we need to tackle. And a number of those optimizations that I wanted to do, I could do with the AST, but surgery on ASTs is just a real pain in the ass. And having SSA based IR makes things significantly easier for optimizations. That's why SSA IRs exist. And so I wanted, as I spoke already when you were here, Ben, I wanted an IR that was higher level than LLVM IR. Jank currently has support for generating CodeGen to LLVM IR. As well as C++ from the AST, but I wanted something that was higher level so that I could do optimization passes on closure semantics. And after looking around, I decided to make my own. Your compiler is ditching AST entirely and directly generates IR from the parser. Cool. AST, I think is pretty important for me. Jank is not only a closure dialect, it's also a C++ dialect. And there's a lot of type checking, overload resolution, template instantiation, everything like that I need to deal with, that an AST is very helpful for. Okay, so here is this. Here's this, and we want to do this, else, and then we're gonna want some way to generalize this block of code that we've copied now in 3 places, but I just want to make it work first. Okay, cool. So there is our if, there's our else, and now we're not doing yet our branch set and our branch get. So we need to deal with our shadow variable. It would be really helpful if we had the shadow information inside of our branch instruction as well. Yeah, I think I'm going to do that. I'm going to grab the shadow information and I'm going to put that inside of the branch instruction. And we'll grab this. Do we always have a shadow? No. No, we don't. Yeah, we don't always have a shadow. So yep, and then IR builder. So we want shadow and here shadow, and then we can pass that through. Cool. So now it's gonna be the same thing. Am I the main author of jank? Yeah, jank is mine. I know there were ads, so I don't know if you cut that RMB, but yeah, jank is mine. I'm the original author, and still the lead of it. At this point, working on it full time. Greatly inspired by John Blow's Jai compile speeds. Yeah, for sure. There are a couple lengths that are really inspiring in that realm. Zig, I think, is also inspiring in that realm. Okay, so if we have a shadow, then we're gonna want to format that in. So we will do auto. Do we do an auto? No. That's what we do. Expert type. Yeah, we don't have the type. I think Lang's with the fast compile speeds can massively change how programming is done. Yeah, I think it really helps. Closure, because we have REPL-based programming and REPL-driven development workflows, is different. So, like we JIT compile a lot of stuff for normal operation, and so kind of incremental builds come as part of that. We don't actually do, like, we don't build an artifact first and then run it. And we do that sometimes, but most of the time we're starting up a process and then incrementally adding code to that process without actually shutting it down by JIT compiling. And yeah, I mean, having fast compilation times still is very important when doing that, but it's altogether a different world compared to just AOT compiling artifacts and then executing them. So I'm going to include some more information here that is not only the name of the shadow, but also the type. And so I think that will give us what we want. And then there was another place I need to IR print. We needed to do this. Yeah, we're gonna need to generalize this more. Shadow sum, shadow unwrap, name. Okay, so there's instruction. So processor, and then, hey, have a good night, RMB. Best of luck with your line as well. So the expert type is the inst shadow unwrap type name. All right, let's try this. Oh, mess something up. IR Builder 99, let's take a look. Ah, right, we didn't go to IR Builder. Yeah, this is the thing about types. Shadow details. Shadow details. Inst. Oops. Okay, and processor IR inst. Inst. Same mistake. There we go. Compiles. Does it link? It links. Perfect. So everything, all that work, we get shadow here that tells us the variable that we're going to be doing our epsilon into, and then ultimately our phi. That allows us to define it here outside of the if. And then what we're going to do now is we're going to assign it inside of each of these branches. So we're going to end up saying we're going to end up implementing branch set now. And branch set is going to set S7 to V10. And so we're just going to have S7 is equal to V10 right here. And then S7 is equal to V13 right here. And then after this, we're going to be able to work with S7 as our result. So let us do branch get. So this one will be inst and b and branch set. So we'll do these both. Actually, we don't even need b for this. I think we can just do inst name for that. And now for this one, we're going to generate some code. What does branch set? It's actually branch set's just void type, I believe. Yes. So we'll just return none for that, I think. And so what we're going to do is we're just going to say this is equal to that. And so we'll do inst shadow is equal to inst value. That's it. That's it. Cool. So now we can get a value, and then depending on the branch, we can set that value to the correct thing. and that is handling our branch set. And our branch get does actually nothing because we already have the value right here and it's already been set. So there's actually no code gen for this. And now we need to continue on to our merge branch so that we can actually have a return nil at the end of this function. And we need to do that right here. So we need to enter our merge block. So I think we can say if inst merge block is sum, whoops, then we just want to do this. So set our block index to be that, and then our instruction index to be 0, and then return. Let's take a look. Nice. So here we grab v16, which is nil, and then we return it. Okay. So this code, we're not actually running any of this code right now, so I'm just compiling it with my mind brain. But everything here looks totally fine. Now, the problem that we get is when we have anything remotely more complex. So, for example, if we had nested ifs, then we're not just going to evaluate one block. So like right here for each if, or for the if and then the else, we're just going to a block, like we're going to evaluate the block, or evaluate, we're going to generate each instruction that's in the block. But it's possible that the body of this if is actually a lot more, you know, it's a bunch of, like, it could be like split under 10 more blocks. If it's a bunch of other ifs, we have no idea. It could be arbitrarily complex, right? And so we need to be able to handle like stepping through whatever is in there. And right now we continue until we're at the end of the block. But what we need to do actually is we need to continue until we find a jump to this merge or a return. Mm-hmm. Yep. And that means that we need to have a way to step that is graceful when it comes to blocks changing. And it means that we need to have a way to peek at the instruction to see if it's equal to a jump to the block that we are expecting us to go to. Yes. Which maybe sounds easy, but is not as easy as it sounds. Maybe doesn't sound easy and is still as not as easy as it sounds. So these are the various logical blocks. So what is our mechanism for looping through? So we have this pattern here of entering a block by name and then setting the instruction index to 0. This probably makes sense to just have the builder have a function called like enter block, which then just takes a block identifier. It does a find block, and then it also sets the instruction index to 0. And then we can just call b enter block here and here, and then in the beginning as well when we were, because we have this sort of same thing done in 3 places. So I see that as a potential change, but that doesn't address the main problem here, which is the iteration until we find a jump. The iteration through arbitrary blocks until we find the jump. Mm-hmm. Mm-hmm. I also think that we probably need to go to having each gen function increment the index on its own. But I'm still not 100% certain. Let's see. Can we just grab... we don't need that. It's just a pointer. So we here want to check if the current inst kind is equal to instruction kind branch and then in here if we really don't need a... Are we going to need a dynamic cast? Can we static cast? Static cast to inst branch. We're going to need IR. Current instant. I think we have a static box cast that we can use. Yeah, nice. We don't actually want branch. We want jump. Jump. Block is equal to our merge block. But we don't always have a merge block. Right now we do, so we can at least assume that to get it working now. So this is our check, and then we break. Do we break here, or do we do our gen for this? the gen for the jump doesn't really do anything. There's nothing to do. So, and then incrementing the instruction index also doesn't do anything because we're just about to change it here anyway. So I think we can do the same thing here. And then if we end up with a more complex case, well, let's verify that this still works. And then we'll end up saying, okay, so yes, still works fine. Now, if I save this, try this. Ho, 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 ho. Let's take a look. So we got a bunch of things going on now, right? Because we have a nested if. And so we end up saying our top level branch is if one and else two and merge three. If one, else two, merge three. But then our if one has its own branch, which is if 10, else 11, if 10, else 11, merge 12. And these use this shadow 16, and then the top level one uses our shadow 7. So here's our shadow 7, and then here's our shadow 16, and then shadow 7 gets equal to shadow 16. Damn. This works. This works. Now the thing that we're not handling yet is doing all this in return position, because we're not going to have a merge block in that case. And so we're not going to have a shadow var. Instead, we're just going to return directly. And our current code gen is going to fail in that case. So I think we should just simplify, go back to a single if, because we're not handling that properly in return position. So let's take a look at this and try to figure this out in return position. Okay, so this actually works nicely as is. So if it's jump, generate it. Cool. Because we end up just generating, like, we just have one block. And so we go through the block, we find the ret. That works. That's not going to work if we have something more complex, I think. But we'll see. Okay. Let's see. Yeah. And so we failed unwrapping an option, and I think that was just the one that I said, yeah, well, we'll unwrap it anyway. I think it's this one right here. Let's see, 440. IR processor 440. Interesting. I think we just can't unwrap here. Damn. Ah. That's great. That is great. Of course, they're like, so we've lost some optimizations. So things like, you know, the deduping of these literals, the lifting of the constants, the lifting of the bars, everything like that. We're just not doing right now because I wanted to get the IR laid out, and then I wanted to get the code gen working. Like on main for code gen in both LLVM IR and C++, we're doing both of these things, but they're going to be straightforward to add to the IR now that we have like a pipeline working. But I actually want to get the full flow going so that way we can get this merged into main sooner. Like I don't want to like get everything to be completely perfect and super fast and everything like that. I want to just move jank onto IR gen and that whole pipeline on main to make sure that I'm not too far away from main for too long, because I've done that. And then other people start branching off of my branch instead. And then when I merge and squash everything, it ends up causing annoyances. This is great though. This actually came together. So yeah, we do have fair amount of cleanup. We have this big chunk right here that is repeated twice, and we want to try to figure out how to like generalize this. I know one thing we can do to clean up these two lines that we repeat is that enter block on the builder. So let's just do that. That's the wrong builder. We actually want this builder. We have a lot of builders. So let's do enter block identifier, IR identifier, block. And we're in a CPP file, so I'm just going to define this in line. And then so here, we're going to grab this stuff. So we're just going to say b index. So yeah, grab the function and then block. Yeah, just that. And so here we're just going to say enter block. That's that. And then here we're just going to enter block. That's that. And then in this function, do we need to use enter block? No, because we are just already starting with whatever the first one is anyway. Okay, this should behave the same. So we don't have code gen for jump normally, but what jump should do is actually enter the block that it is that it's jumping to. So if we did, so here we would just say enter block inst block. And then return none. Like that, I think that should be it for jump. For our C++ gen, we're not actually going to need to do code, like we're not going to need to code gen like go-tos, I think. Because our IR is more structured than that. And that's mainly just because closure is more structured than that. Nice. And I'm not too worried. Those of you who are wondering, like, oh, what about this case or that case or whatever? Like, jank, we already have a test suite for all of this. We have like almost 800 functional tests covering all of these, you know, if in different positions and nested and everything like that, combined with, I mean, every combination you could think of. And so mainly I'm just manually testing these to make sure that things look right. And then we'll, like, once it's ready and we can successfully compile closure core with it, then I can throw it at the whole test suite at it. And that's going to identify any real issues. But yeah, if we can compile closure core and we can pass jank's existing test suite, it's great. It's golden. I'm not a fan of these 2 while blocks because it has 13 lines that's duplicated here. And our goal is basically to just keep iterating until we find a jump. Yeah. I want to just check, does this also work? So if it's equal to 0, if it's equal to 1, if it's equal to 2, and if that's truthy, we return 2, otherwise we return 1, otherwise we return 0. Yeah. That's great. Yeah, I can see how this could be moved into a function that takes the builder and block name, and then it generates until a jump to that block. I just don't know if, like, if it's only in these 2 places in this one function, I don't know if it's actually better to just have it there, like have it written out as is. I think it might be. If this has to show up again outside of this function, then I would refactor it. Okay, so what part am I missing? I felt like we have this in return position with arbitrary nesting. And then also, just to be sure, B. B. So everything propagates up to S7. S7 gets set here and here, not 0. Here gets set to 16. And here's 16. 16 is set here to 36 or 25. 25 is set to 28 or 31. Yeah. Yeah. So we have so we still have try, catch, and case. Is that it? Branch, get, jump. And then function closure and recursion stuff and let fun. Okay. Function closure, recursion stuff, let fun, and try and case. Nice. I think I'll call it here. That's I didn't know how well I was going to be able to actually make it through this this if stuff, because the literature on the literature on lowering like SSA based IRs to assembly and everything is just so dense. I've been trying to do some like cursory research on like how, you know, general approaches, general algorithms, everything like that. And everything is so much more complicated than I think it ends up being in jank. And I think part of that is for sure because Clojure is a language where the instructions that we have are like very well structured, and the, you know, like we don't allow arbitrary labels and go-tos in the language, for example. We don't allow just like arbitrary mutations of things. You know, everything's a function call. And that makes a lot of this stuff just so much easier to reason about. And it allows me to just say like, okay, well, yeah, let's just put the merge block and the shadow block information inside a branch. That way, when we hit that instruction, we have everything that we need in order to piece it all together. For case, we're going to do something similar. You guys probably won't see that because it's going to be another week before I'm on, and I expect before next week, I'm going to have code gen for the remaining things, which was function and closure and recursion, and then try and case, those 5 things. I think I'll have all of those done. And so at that point next week, hopefully, if I'm on track, we will probably step away from the IR for a bit, and we'll actually just start focusing on optimizing things. And that might sound odd because it's like, wait, aren't we doing the IR so that we can optimize things? And yes, but we're doing the IR so that we have the mechanisms that we need to write the optimization passes that we want. But first, like, I don't want to just start writing our optimization passes without like actual use cases of things that we identify. And so I'm getting us to start building from IR and getting jank to use IR. And then I want, as I said, I want to get that merged even before I start writing any optimization passes on the IR. I want to get that merged into main. And that way, all the work we start doing going forward can start building on that IR, optimizing the IR. And there are plenty of optimizations that we're going to do that are not in the IR, right? They're just like general compilation things, or they're optimizations in the runtime or whatever. but we're definitely going to hit some things where it's like, okay, so now we're going to write an IR pass for this. And then at that point, for the first few IR passes we write, we're probably going to identify some things that we don't yet have that we need. Like, we need to understand the dominance of these particular IR blocks or something like that. Other SSA related things that we might need to know. And then we'll go back into our IR processor and we'll make sure that we calculate that information, and we'll use it as needed. But yeah, the main thing is just getting all this set up, and then proceeding with benchmarking things, profiling things, and making optimizations as needed. So hopefully next week we can jump into something different, which is going to be just like profiling some bits of code, figuring out where we need to optimize things, and then doing some benchmarking to see the differences in those results. And we'll see, I don't yet know, we'll actually see when we need to start doing IR-based optimization passes. I don't know. Or maybe I won't be done yet next week, and we'll be wrapping this up. We'll find out. But I hope you guys have a great week. Thanks for hanging out. Make sure you drop a follow, and I'll see you next week. All right? Adios.